All right, thanks for being here once again, folks. We're excited to welcome three of our master's candidates this week. First, we're going to be hearing from Gabby Lund about the Snake River dams, and then we'll have a couple of our other students up next. So we'll have 10 to 12 minutes for each talk with time for a few questions after each presenter. And as always, thanks to the College of the Environment and the Alumni Association for supporting our talks. Take it away, Gabby.
These are always so tricky. Can everyone hear me? No. Can everyone hear me all right now?
Sounds good.
Cool. Okay. Hi, everyone. Like Xander said, my name is Gabby. I'm an environmental studies student in the College of the Environment. And today I'm going to be talking to you a little bit about the Lower Snake River dams, federal dam management, and the U.S. Army Corps of Engineers. So to get started, I want to start with a question. Who here has heard of the Lower Snake River dams? Just by raising hands. That's really good. Who here knows about the issues around the dam management? Some, but less. Okay. I hope then today I'll be able to demystify some of that for you. If you know me, you know I'm a really big fan of really honing in on the story behind an issue. So I think so often as researchers, it's really easy to get caught up in the technical specifics, especially when I've been looking at the data for 2 years. But my hope is to really hone in on the idea of the politics and the drama and the controversy behind it. Scholarly, though. So to begin a little bit, for those of you that don't know, the Lower Snake River dams are located in eastern Washington in the Columbia River Basin. If you're like me and from western Washington originally, I had never heard of it until I went to undergrad over at WSU. But throughout Washington, there's a lot of dams. These include ones that are owned by the U.S. Army Corps, some that are owned by Bureau of Rec, a lot of them that are owned privately from the state, other federal agencies. But this is just a map that shows in the circle where they're at located relative to us. But to get going, it's really important that I focus a little bit on the history first. So there's a lot historically that's happened between the Lower Snake River dams as we know them now and historically. Originally, this all started since time immemorial, really, since people have inhabited the lands. But beginning in 1855 specifically, the 4 Columbia River tribes signed a treaty basically preserving their rights to be able to fish in, quote, all usual and accustomed places with the U.S. government. Don't have enough time to dive into that, but it's an important set dressing for what we're going to be getting into. Fast forward about 100 years, with the Rivers and Harbors Act of 1945, Congress authorized the U.S. Army Corps to build the dams, which then following that, there was a lot of pushback from a number of agencies, including Washington State Department of Fisheries, about the construction of the Lower Snake River dams. There was others, but that's just a notable one from some of the management plans that came up. And then ultimately going into 1956 and into the 70s, the Corps ultimately constructed the dams, drowning these, quote, usual and accustomed fishing places that were originally laid out by the treaties. And then following that in the 60s, going into the 70s, the master plans were produced, which is basically just a series of management plans. And then following the 1980s into the 2010s today, there was a number of issues surrounding ESA listing of salmon species, such as coho salmon going extinct, and then a number of efforts both locally from agencies, interest groups and tribes trying to restore it. It's also really notable because specifically the Snake River and Columbia River, both prior to the construction of the dams, were the most prolific salmon runs in the world, and since then has been diminished. And so fast forwarding to today, there has been a number of legal cases trying to figure out what do we do about the dams and a lot of the biological decline because of it. But for our purposes, honing in on 2018, the master plans that were originally constructed in the 60s and 70s were revised, and a lot of it was to update the evolving goals of the Corps. There was also a number of political actions taken in the 2020s to approach tearing down the dams, but we don't have time to get into that. We'll talk a little bit more at the end. Also around that time in 2020, the environmental impact statement was issued with the CSRO, which is the Columbia River Systems Operations, which included Bonneville Power Administration, Bureau of Rec, and the Army Corps. And then I included this headline, which has some of the political news that had happened locally with the state about pushing to remove the dams. And we'll get into that a little bit more. So, as I'm sure you're all thinking, that was 2024. It's 2025. Things are really different now, especially politically. And so some of the headlines that are coming up now are about how a lot of this push to remove the dams is now being reversed, and what do we do about all that? And so kind of given this set dressing, I was really curious then, what does the literature say? What research has already been done on the dams? And a lot of it I found has been about interest groups, tribes, biological considerations of the salmon, but there's been very little about the Corps' management itself. And so I wanted to hone in specifically on the idea of how does the U.S. Army Corps of Engineers manage the dam, and what do we do about it for the future? So to do this, I looked at the 8 original master plans, or the 8 master plans. 4 of them were original from the 60s, 4 of them updated in the 2020s, as well as the environmental impact statement to do this. And through using Atlas TI, I came up with about 3,000 codes and parsed it down to the one you see in the table above, which included what were the main ideas from these documents. So within the original master plans, the main ideas of why is it managed the way, what are the management factors, were recreation, infrastructure, and land use. In the revised master plans, it was recreation, land classification, wildlife management. And then in the environmental impact statement for resource considerations, it was water supply, hydropower, and fish passage. I also included this image from a protest back from 2017 on the Snake River itself, featuring recreationists opposing the dam, specifically for the reason of the salmon. And so with that, the key themes that came out of my research, preliminarily, I haven't fully finished yet, these ideas around balance and flexibility for the system reliability, tribal considerations, uncertainty, and adverse effects. So within the environmental impact statement itself, there was a number of policy alternatives that the co-lead agencies produced about what do we do with these dams? Given the salmon decline, given the other factors going on, what do we do with all this? So the no action alternative describes the current course of action. The four multiple objectives describe other alternatives of how we could handle it. And then the preferred action alternative is the desired one that the agencies put forth, saying this is what we want to do for the future. Specifically for my research, we're going to focus in on multiple objective 3, which is about breaching the dams explicitly, and was, if anything, the only thing I could find anywhere from a primary source about dam removal, and then the preferred action alternative to contrast these. And so another theme that came up, which I anticipated but surprised me to extent, was how tribal resources, treaties, and rights were discussed. I included a quote here from the environmental impact statement itself, which basically describes how tribes historically have been treated and how actions taken in the past have directly harmed the tribes. But I wanted to contrast that specifically with the stated objectives for the EIS, which included things like improving juvenile salmon, adult salmon, resident fish, the power supply, minimizing greenhouse gas emissions, and maximizing adaptable water management with providing the water supply. And among those, though in a supplementary section, providing better cultural resources was an issue, it wasn't any of the explicit objectives, which I thought was very notable. And then tying in with that, so much of the research wasn't about just what was said, but also a lot about what was left unsaid. And so tying into the idea of uncertainty was how, for instance, things like scientific models were talked about when contrasting the different policy alternatives. So for things like dam removal, when talking about the same model as the preferred alternative, with MO3, the model was described as we'll never really know the full magnitude of what the impact will be. There's a lot of uncertainty around it. Whereas talking about other models, and including the similar model, the way the co-lead agencies constructed it for the preferred alternative was the meaningful contributions that we can infer based off this model. So I'm not an expert in this model. I can't speak with definitive certainty, if you would. But it's still notable to highlight the discrepancies between the two. And there's a lot more. This is just one that I thought really showed it best. And then tying in with that idea of uncertainty, and one of the biggest themes of all was about the idea of adverse effects. And so more than any of the other policy alternatives, MO3 was highlighted to have the most adverse effects on resources, specifically social and economic effects. And this is notable considering how the same EIS also talked about how it would have simultaneously the most biological benefits. And then when comparing that to the preferred alternative, though both co-lead agencies acknowledge that there is uncertainty and there is going to be adverse effects still within the preferred alternative, it was phrased in a way that said we'll still be able to avoid many of these and still really get these benefits that we want. And so what now? Why does all this matter? I think that especially given the current political environment and how things kind of seem futile now for those who are supporting removing the dams, ultimately this issue is going to be inherently political. And though people on both sides of the aisle have been vocal for decades, if not hundreds of years, about how we manage water, it still is a relevant argument to today. And so part of that, and given the criticism of the EIS, there actually was an order to do a supplemental EIS. So basically, they're going to have to go back and redo parts of it. And so with reopening the public comment period to get public feedback on how do we manage the lower Snake River dams, there's also a lot of other movements happening, both politically and advocacy groups to remove this according to their belief. And then one thing else that came up that I thought was noticeable is that for the first time ever, the US government, federal government, acknowledged that the Northwest dams have devastated the region's native tribes. Though there has been discussion about the potential impacts of the dams, there's never been something as explicit as this, and this came out in June of last year. So there's a lot that I breezed through. Does anyone have any questions I can answer? And also, if you want a more extended version of this talk where I'm not confined to 10 minutes, I'll be doing my thesis defense next Friday at 8 a.m. if anyone wants to join, and you're welcome to email me to get an invite. Yeah. Yeah.
As far as research time, how long can you research, many years research to a complete research project?
So originally, oh, yes. So this research project took me, my program is 2 years, but in actuality for this topic, about a year. Before this, I was doing another topic, and then I pivoted about winter last year to this topic.
Yeah. Gabby,
Yeah.
can you maybe tell them what Atlas TI is?
Yeah, so Atlas TI is a coding software. There's a number that researchers can use to code for themes and ideas within it. Specifically with mine, because there was such a volume of the text, there was 1,000 pages. I used a new form within the Atlas TI called intentional AI coding, where basically I provide the research question and a context paragraph about what that research question means. And so it still needs human oversight, but it enabled me to go through a lot higher quantity of document and data sets in a much faster time. Any other questions? Yeah.
Oh, yeah.
I was curious about with the role of the US Army Corps, how that, it seems as though that has been a prevalent focus for you. Like, what has that actually, what have you seen about their role that may have been like surprising or concerning in a way of like, oh, this is some change or anything like that?
That's a good question. So the question was, what has been surprising for me and has stood out about the Corps? I think what really has been the most surprising to me is with my research, oftentimes as scientists, we're focusing on what's said, what's there, but equally important I've noticed is what isn't there. And it's not that I'm over extrapolating what isn't there, but it's more of like I was pointing out earlier in the presentation, small discrepancies where if you're reading or scanning through it, you might not notice. But when you really get granular and begin noticing, well, we talk about uncertainty here, but in a very similar facet, it's very different in this other paragraph. And using that to figure out what is being said, but also what is more implicit to the documents. Any other questions? I'm going to take it as I did a really good job.
Hey, thanks, Gabby. You want to hand that off? All right, we're going to do some. The same format for questions here in 10 to 12 minutes.
All right, thank you, everyone. And good job, Gabby.
You're on.
Okay, I am. My name is Bo MacArthur, and I'm a grad student in the Environmental Studies Department here at Western in my second year. And my thesis is titled Quantifying Irrigation in Washington's RIA 1, which is Water Resource Inventory Area, where I'm using a field scale method to quantify irrigation in the absence of ground measurements like water meters. So I'll start with a quote from, sorry, they got a pop-up coming here. Okay, start with a quote from Luna Leopold, who was the first chief hydrologist at the USGS. And I think it's very applicable today, especially because all three of us that are talking, our theses are focused around water as a central theme. Water is the most critical resource issue of our lifetime and our children's lifetime. The health of our waters is the principal measure of how we live on the land. Okay. Water is a fundamental resource that we depend on for food production, industry, energy, as well as many other things, the health of our ecosystems. And the significance of water use in global food production especially cannot be overstated. Estimates vary, but about 70% of global freshwater consumption is used for agricultural irrigation. In some regions, that estimate can be as high as 97%. And freshwater resources, due to population growth, locally, regionally, as well as globally, and climate changes, are putting increased pressure on our limited freshwater resources. So having reliable monitoring techniques are needed to be able to efficiently manage these resources so that we still have access to them now and then into the future. So I mentioned Water Resource Inventory Area 1, RIA 1. That's where we are here in Bellingham in the western part of Whatcom County. So Washington State freshwater resources are managed within these distinct areas called RIAs. There are 62 of them in Washington. They are geographical areas that are, or geographical political administrative areas that are loosely based on topographical features and watersheds. In the case of RIA 1, the primary physical water feature is the Nooksack River with its three forks, the north, middle, and south fork of the Nooksack. So in green here on this map is the extent of irrigated fields in RIA 1. There are about 100,000, there are over 100,000 acres of farmland in RIA 1 with about 1,500 operating farms, with the most prevalent crops being food production being dairy, berry, especially raspberries and blueberries, and then potato seeds. So RIA 1 adjudication. Adjudication is a lawsuit in a nutshell. It's a lawsuit that is currently with the Whatcom County Superior Court. It was filed with the Washington State Department of Ecology against all water users within RIA 1. And its purpose is to legally clarify all water rights. It is a very long process, potentially decades long. The last water rights adjudication in Washington State was in the Yakima River Valley, which took over 40 years to resolve. It resolved around 2019. Once that was resolved, there was a couple-year period where the Department of Ecology was searching for the next place in Washington that would be most appropriate for an adjudication, and RIA 1 was selected. The adjudication was officially filed last year in May, almost exactly a year ago. And in order for this process to occur in a timely manner to organize and quantify all of these water rights, clear, consistent water use data are needed. Managing water in RIA 1 is not easy for several reasons, both physical and social and political reasons. So a physical aspect is there are disparities in seasonal flow. This is a graph of the discharge of the Nooksack River at a stream gauge the USGS has put in and monitored. And you can see that in the wet winter months, there are these really large peaks of high flow, followed by, on the left side of the graph in green there is the summer months, the growing season. It just continually goes down. And as climate is changing and more precipitation is falling, as water rather than snow. We're seeing this trend of higher peaks and then lower summer flows, which makes managing water difficult because more water for irrigation is needed in these drier summer months. From the social political side, water rights are messy, often unquantified, unregulated, and really hard to keep track of. There's lots of they've changed a lot over time. There are about 5,000 individual water rights is estimated, and there's poor documentation, poor regulation. Some farmers are operating with no water rights or unclear water rights. There's also this concept of first in time, first in right. So if water right holder A is entitled to 10,000 gallons and water right holder B is also entitled to 10,000 gallons, but the water right A was first, that is first in time. And in a season where there is limited water available, water right holder A is entitled to take every drop that they're entitled to before water right holder B is entitled to take a single drop. So it's really important to get all of these water rights not only quantified, but also lined up in time so that we know who has precedent and which water rights are senior to more junior water rights. But again, there's a lack of cohesive and comprehensive water use data. That is what this adjudication process is meant to do. It's meant to unravel all of this. So where I come in is trying to fill in that gap of creating comprehensive water use data. And there are a lack of meters. Meter use is really hard to, meter data is hard to, it's expensive to install meters. It's expensive to extract those meter data. So another way to do it is using GIS and remote sensing techniques with these inputs. So evapotranspiration is a combination of evaporation from the ground surface, transpiration from plant leaves, precipitation is the input that goes in, and then to quantify that spatially, we have field boundaries and water meter records. So in my research, I gathered an extensive data set from the Department of Ecology of water meter records to use as ground truth data from which I would validate the models that I will explain next. And this map here shows the spatial area of where the water is being used. So it's called a water right place of use. Meter records are really messy, and this table schema shows that briefly, where there's sometimes 3 or 4 meters associated with sometimes 7 or 9 water meter records. So figuring out where the water is being used from water meters is difficult. So I built some models to try to create a unified, comprehensive way to measure irrigation. And the first approach I took was just a comparative analysis between an irrigated field and a neighboring non-irrigated field. So this diagram explains on the left-hand side, we have an irrigated field that has water inputs being precipitation and irrigation, with an output being evapotranspiration. So that's all water that is leaving the ground or the soil surface or the plants into the atmosphere. So we would expect that an irrigated field would have more water, more evapotranspiration leaving than a nearby than a non-irrigated field. So we can take, using a intimidating looking equation that is actually not as complicated as it may seem. It's just taking the difference between the irrigated and the non-irrigated fields. And the difference there should be taken up by the quantity of irrigation. So that's one approach. The other approach I use is a little bit more complicated, based on a soil water balance approach. And this looks at all possible inputs and outputs to the soil water balance system. So on the left-hand side, inputs, again, we have precipitation, irrigation, and then an additional stored water. So there are some months, especially now where we are here kind of in May, June, where it might be a dry period, but it was preceded by several months of wet weather. So there's still going to be some amount of water stored in the soil that plants have access to. Then we have transpiration and evaporation as the 2 outputs into the atmosphere, but additionally, there's runoff and deep percolation. Not all rain that falls in the ground is available to plants. Some of that runs off into streams, some of that percolates deep into the soil. So there's another intimidating looking equation here, but essentially this model is like a leaky bucket. So if there's a bucket with some amount of water that has two holes in it, that water can also evaporate out of, precipitation and irrigation will be the inputs to the bucket. Runoff, depercolation, transpiration, evaporation, those are all the outputs. And that bucket can't have a negative amount of water volume. So if this equation becomes negative, then, and we don't know the amount of irrigation, that negative amount must have come from somewhere else that is not a natural source of water. So it must have come from irrigation. That's the basic conceptual thinking behind this model. And this model uses a machine learning approach. Depercolation and runoff especially are very hard to measure physically because it involves a lot of different inputs. So these constants in this equation, x and y, can vary. They can vary monthly, and they can vary anywhere between 0 and 1. I'm not going to get into the specifics of that, but there would be 1 followed by 48 zeros, which is an incomprehensibly large number of possibilities to optimize this model, one version of this model to best fit the water meter data. So I used a machine learning approach to optimize this model and then a few versions of the soil water balance model, where it would run trials automatically using different inputs for these different constants that go into the equation, and then tracking the objective value, which in this case is minimizing the error between the predicted model results and the actual metered results, or the metered values that were measured from the ground. And it learns from this, and it continually makes more predictions to try to minimize the overall error. And I did this for several different models, found the model of best fit, and then also compared this with the first model that was just comparative between irrigated and non-irrigated fields. The ultimate goal is to develop a web application, which I have a proof of concept version of right now through Google Earth Engine, where a user, farmer, policymaker, someone at the Department of Ecology that's working in the adjudication can use a tool like this. They can click on a field, they can get field properties, the crop type, irrigation volume, precipitation volume at a monthly scale for each individual field. And then they can also see how the irrigation quantity has changed over time, and then take that data and download that data. And I hope that the results of this research will have an immediate effect in this adjudication process. The first adjudication forms are they're due next May. Then following that, there's a 3-year period for anyone that has filed a claim to submit proof of their water use. So this will not be the only way that people can prove water, but I do hope that it is an additional way to help provide some clarity to an otherwise very complicated and potentially decades-long process. All right. And yeah, I know that's a lot in a short amount of time, so I'm happy to answer any questions. Yeah.
Given that adjudication is civil court and the standard for evidence is the preponderance of the evidence, how would you rate the quality of evidence coming from your model here on a scale of personal affidavit to meter data?
Yeah, it's a good question. So the question was, this is a civil case, so how would I rate the quality of evidence that my model will produce on a scale of affidavit to water meter data? It's a good question. And like I said, and I guess I touched on at the end, I don't think the results from this model will be accurate enough to be the only evidence that someone will present. But I think the biggest benefit of this is it's a cohesive, unified way of measuring water across a 13-year period, which is my study period, at a monthly scale for all fields measured in the same way. There's so much discrepancy in water meter data, especially that I've seen while working with the data and trying to clean it and make it fit into a monthly box, you know. So I think this paired with affidavits, written affidavits from neighbors, aerial photos, and what other evidence that actual water users have, I think this will just be like a little nudge to hopefully help clarify the whole look at the system. Yeah, it's a good question. It's an important question. Yeah.
Are the equations that you use like standard in your field of study, or are they mathematical models that you like created yourself?
Yeah, that's a good question. So the question was, are the equations standard and used throughout this field, or are the mathematical models that I've developed? And the answer is a little bit of both. So specifically the soil water balance is there's soil water balance equations that have been used extensively in hydrological modeling and this type of research. This is an equation that I have made that is unique. So it is something new, but it is heavily based on previous work and previous research in this field. Yeah. Yeah, I'm back.
How did you get into this?
Sorry?
How did you get into this?
That's a good question. The question is, how did I get into this? I came in, it's a long version of this answer. I'll try to make it short. I came into this program wanting to use GIS tools. I always had an interest in remote sensing. And I also really wanted to do something that had an immediate impact. And this kind of fit all of those criteria. So yeah, that's the short version. Thank you.
Yeah. When I clip it there, it's got a low battery too, so we'll find out.
See how it goes. Anyhows, to set the stage for invertebrates in the lower Snohomish estuary, I want to talk about estuaries and salmon in Washington state. And the picture here is of the lower Snohomish, my field area, but salmon are using estuaries across the entire state as a vital stopping off point during their spring out migration period. And this graph is some data that has been collected in the lower Snohomish showing Chinook salmon usage of the estuary. You can see that the Chinook salmon are peaking in their abundance in the smaller estuary blind channels in April, and then peaking in abundance in the larger distributary channels in May and June. But they're heavily utilized in the estuary, and they're utilizing it because they love to eat estuary invertebrates. Their entire goal while they're in the estuary is to get as big as they can, because if they don't get big in the estuary, their odds of survival go way, way down once they exit into Possession Sound and the rest of the Salish Sea. And the invertebrates we've got up here, we've got an amphipod at the top, we've got some insect larvae in the middle, and some chamations at the bottom, which are all favorites of the little juvenile salmons. Now they've got one problem, which is that we've destroyed a lot of the estuary habitat in Washington state, and it's estimated that up to 90% of the estuary habitat in the lower Snohomish had been destroyed at a certain point. Thankfully, since the 1990s, there's been a big push to restore a lot of these dikes and breach these dikes. This push has been led in large part by the Tulalip tribes, who are our project sponsors and also our partners in this research. But just to talk briefly about what it looks like to restore an estuary area, the dike is outlined in red there, and then the green arrow is pointing to where the dike has been breached and where channels have been dug up into the restoration. And at this particular restoration, that allows the area to be inundated with water from EB Slough and any invertebrates or fish that come with it. And our sampling site in this particular restoration is the sun, because of course it's always sunny when we're doing field work. It's the only lie I'll tell today. The goals of our project are to understand how the community of invertebrates is dispersed across the lower Snohomish estuary, what the composition is at some of these restoration sites, and then to look at two timescales, both the small timescale of tidal and single ebb tide variability, but then also look at variability across the entire salmon outmigration season from February through June. And lastly, it's our hope that invertebrates can be used to demonstrate restoration area success in the lower Snohomish. And sampling in a tidal system means that we're sampling in a system where the water height changes considerably in a very, very short time period. And so at high tide, you can see that the marsh surface is completely overwatered. There's just some little islands popping up with vegetation. And then as the tide drops, all of this water becomes channelized into the estuary channels. So when we can start sampling. And then we sample until the water has completely run out of the channels. Just a little trickle remains at low tide. And there's very little export of invertebrates and understandably no fish use. And the method we use to do this sampling is noosed net sampling. We erect two vertical posts and then we put our noosed nets, which noosed is any loose organic organisms within the water that are getting flushed into our nets on the ebb tide. We drop a net down into the bottom of the channel and then we float a net on the surface. And because it's floating on the two posts, it can track the water level as the water level drops in these channels. And we sample only for 10-minute durations, but sometimes the water can drop during this 10-minute duration 10 to 15 centimeters. And so we track the water level as it drops, sampling until there's no more water left in the channels. And just to present some preliminary results, of course, this research is ongoing, so these aren't finalized, but in the bottom of the graph here, we've got our elapsed ebb tide. Basically, the ebb tide is progressing, the water level is dropping in the channels as the percentage of elapsed ebb tide increases. And then we have our invertebrate abundance, which has been corrected by cubic meters of water in our sample. And while the magnitude of the increase in invertebrate abundance does vary between three of our emergent marsh sites here, the trend remains largely the same, which is that as the water level drops in the channels, we are seeing more invertebrates being exported out of those channels within the water column. And this increase appears to largely be composed of amphipods, the red, Comatians, the sort of golden brown, as well as fish larvae and mysids in green and pink are also contributing to this increase in abundance within the water column towards the end of the ebb tide. Now, looking across the entire outmigration season, last year we were only able to sample from April through the end of June, and we were only able to sample a single one of our sites, the Quaalude restoration area, enough times to really make a graph that looks good over the whole outmigration season with enough data points. But what we largely see here is solid abundance of invertebrates within the Quaalude restoration area all through April, through the end of May. But then in that final week of May, first week of June, we're seeing a big drop in invertebrate abundance, and that drop is carrying through the end of the outmigration season. And the orders of invertebrates I've included here are 5 orders / clusters of orders that are relevant salmon prey, and especially amphipods, Comatians, and mysids are seeing significant decreases in their abundance towards the end of the salmon outmigration window. Like I said, this research is ongoing. We started our field season this year in February, and we're going to run through the end of June again. So we're going to capture the entire outmigration window instead of just April through June. And we also added another site in a region of the Snohomish that has not experienced any diking. So the channels there are naturally formed. They aren't dug like the restoration area channels are. In addition, we're going to be assessing the energy density of these invertebrates so that we can draw a direct line from the count of invertebrates in a channel on a given day to the amount of calories that are available for consumption by juvenile salmon. And lastly, when we look at trends that are occurring across the whole outmigration season, we're hoping that we can align those trends in invertebrate abundance with trends in fish abundance, because we believe that our sampling might be at a fine enough resolution that we can capture predation of the invertebrate populations by juvenile salmon, but also by marine fishes, which are heavily using the estuary during this time. And I'd like to thank this laundry list of students, graduates and undergraduates here at Western who have made this research possible as interns and volunteers. And I also want to thank NOAA Fisheries and the Tulalip tribes, because without their consultation, financial support, and support in field work, we would not be muddy in the estuary and none of this data would exist. So I want to shout them out as well. And yeah, I'll take any questions. Yeah, way in the back. So for our online friends, the question was, do I have any guesses as to why there's a drop in invertebrate abundance in May and into June? I think at this point, it's too early to say, but we certainly expect that when we look at fish abundances, we're going to see increased fish abundance during that time. And just from being in the field on those particular sampling days, I can tell you there was significant activity of marine fishes in the channels on those days. So that's very anecdotal, but we expect to find a link between fish activity and lower abundance of invertebrates because they're all getting eaten. Yeah.
Like fish abundance, that data that you're going to collect yourself, or are you looking to other places to sort of compare?
Yeah, certainly. So the question was, when we're looking at fish abundance, really, where is that data coming from and where are we going to look for that? There's a couple different stakeholder groups that survey fish within the Snohomish, the Tulalip tribes being the primary group. And so they hold all of the fish abundance data for the region of the estuary that we sample. And in fact, they sample fish in several cases only a couple 100 feet away from where we're sampling invertebrates. So we expect to be able to make a pretty good comparison at all of our sites.
Have you got to interact much with them while you've been working, or just doing your separate things?
The question was, do we get to interact much while we're working? And the answer is yes. They, in some cases, are sampling fish on the exact same day that we're sampling invertebrates. We even ride the boat out to one of our sites with them when they're sampling fish. So it's very hand in hand, and it's been one of the great parts of this project to work with the tribe on that. Yeah.
Measuring the caloric density of fish, or I guess not fish, invertebrate.
The question was, how am I measuring the caloric density of the fish? We use something called ash-free dry weight. Basically, we aggregate, for example, 200 amphipods into a porcelain crucible. We dry it out for a week in a drying oven, and then we weigh it before transferring it into a muffle furnace where it burns at 500 Celsius for 3 hours, and that reduces any organic matter that was in the crucible to ash. And so by weighing the crucible after it's been in the muffle furnace, we can subtract the ash weight from the dry weight to get a measurement in grams of how much organic matter is present in those invertebrates. And then we can convert that organic matter in grams into kilojoules and calories. Yes, Anthony.
identify any of the fish species in these channels while you've been sampling?
The question was, have we identified any of the fish species in the channels while we're sampling? Absolutely, yes. Occasionally they swim into our nets, but not often. And you can see, certainly we've been seeing this year, large schools of juvenile salmon swimming right around our nets. And the marine fishes, some of them are on the slightly larger size, like maybe 5 to 6 inches long or 7, 8 inches long. So they're very visible when they're swimming around in these channels that are only, 8 to 10 feet deep and maybe 15 feet across. Yes.
Do you eat a lot of seafood during this
The question was, do I eat a lot of seafood during this time? Honestly, during the field work, it's fine, but as soon as we get them in the lab, we preserve all our samples in ethanol, and they do ferment a little bit, and so I have to lay off when I'm doing the lab work because I can't look a shrimp in the eyes. No other questions?
That's a good place to leave it. Thanks, Sean. All right, thank you again for being here, folks, and we'll see you next week.